Hello students, this is the video for the geology of terrestrial planets. I'm too tired for this. What you're seeing here is a volcano. All right. And since it's pretty up close, you can imagine it's on Earth. We're going to talk about how the surfaces of the planets, now the interiors of the planets, are constructed and how we understand them. Computer, you need to go forward. There we go. So, all right, we're going to start on the inside and then work our way out to the surface and talk about the surface. So we can see some of the surface, and there's some things. This is one of those things that in physics, this is what's called the inverse problem. Is a lot of times when we solve a problem in math, we're trying to take some initial conditions on the inside of a thing and develop what's going on the outside. But in physics, we do it backwards. We see what's going on the outside and try to figure out what had to happen on the inside that we can't see. We try to invert the normal problem. We take the effects and try to find the causes. And so with the planets, we can see the surfaces very easily, and we're trying to figure out what's going on the interiors that allow for the exterior properties. So a lot of what we find out about the Earth, about its interior, is from earthquakes, which, seismic waves. So we talk a little bit about how earthquakes propagate. There's two types of waves in general. There's what's called transverse waves, where any particular part of the wave moves perpendicular to the direction the energy moves in. And that's, in this picture, is going to be called the S waves. And you can think of that as side to side, as you move up and down in the picture and the energy moves to the right. The other source was called longitudinal, which is along the direction that the energy moves in. And so in this picture, it's what's called P waves. For you can think of it as pushing and pulling waves. The particles move left to right, and the energy moves to the right. So these two types of waves both propagate through solid material. And what we find is that inside the Earth, by measuring the properties of the waves that we see, that there has to be some sort of solid-ish core that's mostly metal, very high density stuff. And then as we go outwards, the density drops. The mantle is going to be medium density. It's going to be stuff like silicon and oxygen compounds, minerals, effectively. And it's going to be somewhat liquid. And then at the core, it's going to be solid again. It's going to be low density stuff. It's going to be stuff like rocks. And we figure that most of, that the other planets should be mostly like this. We have reasons to think Mercury is going to have a very big core, and Mars and the Moon are going to have very tiny cores comparatively. But in general, this sort of crust mantle core construction is what the terrestrial planets look like on the inside. Now, the reason they're separated out by density has to do with their formation, that they were molten and high temperature when they formed, because all of the energy from the accretion process is going to heat up the planet. And so it's very easy for liquids to separate out by density, and the molten metal is going to separate out in the same way. The high density stuff falls inwards to the core, and the low density stuff floats and rises up to the surface. So this process is going to show up in more places in the universe, but we see it first here in the terrestrial planets, the differentiation of layers by density. So the outer layer that is cool and rigid is what we also call the lithosphere. And it's the bit that floats on the more fluid rock underneath. And that's the thing, rock is not completely solid. You can think of it more like silly putty. Silly putty, if you try to snap it in half, you can break it, but it's also nice and stretchy too. Right? And that's a matter of, are you pulling it fast or slow? Right? So gravity tends to be a force that can act very slowly, and it can deform rocks, and basically it forces large enough planets to be spheres. If the gravitational force is small, like on an asteroid, you just get a potato shape. The material strength is high enough to just hold it in shape. But for a large object like a planet, it's going to slowly pull all the material into a spherical shape. Right? So, how do we actually know that there's liquids and solids inside the Earth's crust? Well, the two types of waves that we've seen don't propagate the same. P waves can go through the Earth's core, but S waves can't. What we end up seeing is, if there's an earthquake, there is a shadow where we don't see S waves. And that gives us a rough estimate of the size of the core. And it also tells us that it's most likely a liquid outer layer. The idea is that S waves are side to side waves, and those waves don't propagate through liquids the same way that P waves do. Pushing and pulling is fairly easy to do in a liquid, but shaking side to side is difficult, if not impossible. And so you're left with only seeing the P waves in a certain region, which tells you roughly the size of that core. So we got to talk about how this actually happens. These are processes that use energy, and we also need to talk about those processes in particular. But we need to talk about where that energy comes from and what's going on. So the interiors of planets are hot, and that energy has to come from somewhere. So early on in the formation of planets, it's going to come from the formation energy. Is that all of these rocks that are accreting together, all these planetesimals, are going to have high kinetic energies. And when they collide with each other and eventually form a planet, that kinetic energy, the kinetic energy is going to eventually turn into some of the kinetic energy of the planet and some of the internal energy. It's going to heat up the material. Falling material inwards towards the center, the differentiation, is going to take gravitational energy and turn it into internal energy. So that's good for the very early portions of a planet's history. But now, the biggest thing is most likely to be radioactive decay. In the core of the planets, we're expecting very high density, high mass metals. And a lot of those metals that persist, the heaviest things, are going to be radioactive. And so that radioactive decay is going to continue to produce heat today. So that's the heat sources. When it forms, it's the formation energy, the accretion and differentiation. Now, if there's energy being formed, it's decay. So planets lose energy, and any object loses energy through these three methods: convection, conduction, radiation. So the different layers are all in contact. Heat can conduct from atom to atom, from lump of stuff to other lump of stuff. They can conduct, as long as there's a contact path, heat can conduct. If there's a liquid or a fluid layer, heat can convect. There can be hot material that floats because it's lighter density, and then it gets to the surface or to the point where it stops moving and cools off, and then it's now heavier density and it sinks back. And so it circulates, it convects. Eventually that heat gets to the surface and it escapes the planet by radiation. The surface glows in infrared. Now, the rate at which it loses energy, it depends on how much energy it originally had and how fast it can radiate it away. So what we see amongst the planets is the smaller worlds like the Moon and Mercury are basically cool. There's no leftover heat. Whereas Mars, maybe there's some heat. We're not certain, but there's probably some heat remaining. And the Earth and Venus probably have a significant amount of heat left over. The obvious differences between these, the Moon and Mercury are small, Earth and Venus are big. Size seems to have some role in it. And what we find is that the total heat depends on the amount of material. Like the original heat and the amount of radioactive decay is just a factor of the mass. And so the heaviest planets are going to have the most stuff. And so in terms of the size, heat content depends on volume. But the radiation can only happen at the surface, so it depends on surface area. So we can look at the ratio between the volume and the surface area, or we call the surface area to volume ratio. And that happens to be 3 over R. And I've shown the math here in this slide. So the larger the radius, the slower a planet cools off. And that matches what we've seen. The smaller planets have a smaller R, which means they have a larger ratio. They cool off faster. So there's one more thing going on with the interiors, and the effect we see is that there's a magnetic field around planets. So some planets. So we need to talk about magnetic fields. And to super simplify it, because in physics, the truth is we don't exactly know where magnetism comes from, but on a big scale in a lab, it comes from the motion of charged particles. All right. So that's the thing, is that you can always ask why, and so at some point it gets down to I don't know. When we start asking about magnetism, we can talk about charged particles, but we don't know why charged particles give off a magnetic field. Or why moving charged particles. That's kind of the important thing. It's got to be motion particles. And so when we look at what's pictured here is an electromagnet. You have a battery and a coil, and there's a magnetic field around it, and it looks suspiciously like the magnetic field of a planet or of a bar magnet. And we can explain, the features of a bar magnet. There's atoms, they're arranged in some sort of lattice and as a crystal, or some sort of set of crystals in a material, and you line up magnetic moments, and you end up with a magnetized object. And those magnetic moments look basically like the alignment of the atoms, which represent electrons going around in a circle in some way. So in a planet, it's kind of, well, what's going on in a planet? Well, planets have electric currents in them. They, you can measure some of them by basically measuring the current passing through the dirt at the surface. But in general, what we think's going on is you have a molten and conducting interior. Well, the Earth has that. You have some sort of convection to move the material around, and you have some rotation. That's what we think you need to have a magnetic field in a planet. If you have that, then you can have charges moving, basically orbiting the core, and that's going to generate this magnetic field that you see around it. All right, so magnetic fields that you see tend to be based on currents that are flowing in a loop in some way. So, with that, we see the terrestrial planets that are rotating fast, like the Earth and Mars, are going to have some magnetic field. The ones that rotate slowly, like Venus and Mercury and the Moon, are going to have much, much less or no magnetic fields. So that's the interiors of planets. Here is the surfaces. Basically, four things can affect the surface. One is that outside objects impact on it and just smash it up and it leaves craters. One is that the interior leaks out. Molten rock comes to the surface and makes new surface. That's volcanism. The interior can also put stress on the surface, and so you'll see bending. You'll see formation of mountains and uh, and valleys and such. That's tectonics. And then you can have wind and water and ice erode the surface. Right, so cratering, it looks like an object hitting a surface, and it leaves a depression, a bowl shape, where you've moved rock away. Most of this cratering happens when there's lots of stuff in the solar system in the early times. Craters are going to form mostly when there's stuff around to impact. And so, in general, what we see, craters are about 10 times the size of the thing causing them. And there's going to be lots more small objects, and so lots more small craters than large objects and craters. So here's a few examples. We don't see that many craters on the Earth. If you did the cratering activity as the optional, I ask you a question about the number of craters in Texas, and you would expect something like a few hundred, but there's only like 3. But there are some that persist. Meteor crater in Arizona is fairly large and deep. There are several others around the world, but there's just not as many as you'd expect. For a lot of craters, you kind of have to go to the moon or to Mercury, and so on the moon, you kind of get the classic crater shape. A nice spherical shaped bowl with sometimes you'll see a little ridge of material pop up in the center. Yeah, I'm also running office hours while I record these, so you need to, sometimes I'll pause for a moment and it won't make sense if you hear a glitch or something, just so you know. Let's see. So different types of craters depend also on the surfaces and the other effects going on. A typical sort of crater into dry rock is going to leave, a bowl-shaped depression, the standard crater, and a ring of debris around it. where you can also have craters in ice or in muddy, waterlogged soil, and it's going to leave obvious signs of not being a perfect crater. And then some craters can be eroded. You can see the evidence that the nice sharp shapes have been smudged out, and you're just left with debris. All right, so anywhere where the interior liquid material can leak out to the surface, it's going to cause volcanism. It doesn't have to have a volcano, it just has to have that leaking. And so the interior liquid is called magma. If it finds a path to the surface, then we call it lava. And so you can have lava flows. Now, oftentimes lava flows will cool and harden and form volcanoes, but not always. It depends on the thickness of the liquid. So, for example, on the moon, there are lava flows that leave very flat plains that basically fill in craters and valleys. And what's happening is the magma is extremely runny. It's a very low viscosity, and so it just oozes out and spreads large distances before it cools. And so you form very nice flat surfaces, and they look dark compared to the surface that's been broken up by impacts. And so when you look at the moon, there's very bright surfaces, which are crater remnants and dust and, lots of broken up surface. And then there's dark maria, which are the lava flows. So slightly thicker, slightly more viscous lava is going to flow fairly large distances but cool, and it's going to build up a mountain. And so they make these broad shield volcanoes. And Mars is an ideal example because it has massive, massive upwelling volcanoes. These massive shield volcanoes. The big example is Olympus Mons, which I think is the largest volcano in the solar system. Vaguely sits slightly outside the atmosphere of Mars. Mars's atmosphere is fairly shallow and low pressure, and this is a huge, huge volcano. So we see a few of these on Earth. Earth has even thicker, more viscous lava, and you can build up steeper stratovolcanoes. So I'm sure you talked about this in some science class in middle school. But the gist of it is different types of volcanoes are coming from the thicknesses of the lava that can flow. Volcanoes also put gas into the atmosphere that's formed in the interior. So, in some cases you see, huge clouds of ash and gas emitted during an eruption. In other cases, it's just a slow leak of gas coming out of a vent. So the region under the surface is going to experience convection, and that's going to cause stresses on the surface, and that's tectonics. So in some places, the convection is going to push by friction. It's going to push that upper layer together, and you get mountains. And in other places, it's going to stretch it apart, and you get valleys. We're here an example of tectonic stresses that are pushing together, and the Appalachian Mountains have formed, and they're slowly being eroded away. But they're a wrinkle in the surface is pushed forwards. valleys form, and we also have a picture of valleys on Mars where the material has stretched outwards and pulled apart the surface. So this is distinct from plate tectonics. Um, Earth is unusual in that we notice the crust is in significant chunks called plates. Um, and we can see some evidence where some of the, if we look at the mountains that are around, we still see some evidence that um, the the mountain chains could connect together in the past, and the land masses could fit together in different ways. South America looks like it should fit right beside West Africa. The Andes and the Atlas Mountains and the Himalayas kind of look like they could kind of link together, and the Appalachians and the Alps are kind of like that. And effectively, we see some evidence of the continents can be put together in a sense. And what's happening is that these plates have moved over time, and we can see the directions of some of the motions. The the different plates here are going to be divided by mountain ranges and ridges in the ocean. And what we're seeing, we see evidence the Pacific is moving under North America, or North America is moving over the Pacific, and India is moving up under the Himalayas. And you have a chunk of East Africa is moving westward, it's being pulled apart. We have different, lots of different ways that the plates are slipping and moving around. And erosion, any sort of thing that breaks down and transports rock around is erosion. But in general, we can identify as weather, things like glaciers and rivers and wind. Ice and water is going to move rock around and break it up. And so, of course, on Earth, there's plenty of erosion because there's plenty of weather to drive erosion. The Grand Canyon is a big example. It's close to a mile deep, and it's been cut by the Colorado River over time. Glaciers carve out valleys, and here is the Yosemite Valley. It's had a glacier cut through it. Deserts with sand dunes are the wind is breaking up the rock and carrying the rock away as sand. Rivers dump out sediment and form new land. All right, so we'd like to try to figure out the age of a surface. We can figure out the age of the solar system from radiometric data, but that doesn't tell us, it doesn't tell us when a surface forms. That tells us when the atoms showed up. So surfaces can form at different times, and we'd like to know when they formed. And the gist of it is usually we kind of know when most of the cratering happened, and we can figure out the rate at which craters tend to happen, the rate at which impacts happen. And we can figure out the effects from the other geologic processes. And so we can age a surface by craters. Most of the craters occurred in the first billion years of the solar system. And so if there's a lot of craters present, then there's not been a whole lot of change to the surface, which means it's an old surface. And so in general, there's a whole activity on counting and aging a surface. But in general, the trends is we see old areas have more craters, especially when there's no erosion or volcanism. On the moon, there's lava flows that are going to wipe out some craters. And so those lava flows are younger than the cratered areas. So here's the entire surface of the moon, and you can see lava flows that have formed. And you can see in areas where there's very bright cratering, there's lots of craters. Those are old surfaces. But in the areas in the center of the picture that are darker, there's very few craters, and so those are much younger surfaces. So the planets are different effectively because of the amount of energy they have and the processes that are going on the planets. Right? Is effectively small planets have less energy. They cool off faster, and effectively they get set. They harden up. So you don't get internal processes like volcanism or tectonics. Larger planets can do that. They stay warm inside. And larger planets tend to have more atmosphere, and so they have more weather. They have more erosion. There's a few other things. If you're close to the sun, there's less likelihood of weather because it's too hot. If you're far from the sun, the liquids are going to freeze up, and so there's less weather. Hot planets tend to not have atmospheres, or like Venus, have very, very insulating atmospheres. But planets far from the sun are not going to have very much weather because it's too cold. Basically, you want to have liquid water to have the most erosion. There's some other stuff. Slow rotation means the atmosphere has less energy, so there's less weather. Venus has a very thick atmosphere, but it can't do very much with it because it's basically stationary. Fast rotation promotes more weather, promotes more erosion, and you have a strong magnetic field, which tends to mean that you keep an atmosphere better, which we'll talk about in the next chapter. So, this is where we go through and talk about each planet individually, and we start with the moon, which obviously is not a planet, but we're including in it because it's a rocky object. And what we see there is lava flows. Right, we see very minimal cratering in these lava flows compared to brighter areas. And in general, they're just runny lava has oozed out of the surface and formed these flat areas. So early, there's going to be lots and lots of craters. One large impact, though, weakens the crust, and the heat that's built up there allows lava to break out. And so you're left with the large crater is filled in with a lava flow. There's some evidence of tectonics, basically wrinkles in the surface. Mostly they're in lava floods where the cooling causes a contraction of the surface. And for the most part, it's very stationary. The biggest process now is tiny impacts, tiny meteorite impacts, which are going to break up the surface. The surface is kind of like flour. It's very, very fine. You can see the footprint that's here from the moon, we've left this footprint that's basically like stepping into a bag of flour. Not much changes. The surface is basically dead. There's no new. The only new process is continued impacts. All right. Mercury is going to look fairly similar, except maybe more extreme, because it is larger and it's closer to the sun, and there's more interesting stuff that can go on. Effectively, lots of cratered regions and lots of smooth regions where there appear to have been lava flows. And so here is a large impact crater on the left, and you can see the smaller impacts that have occurred later on top of it. And in some places, craters leave hollows where there's escaping gases coming out of the crater. And one thing we see is that Mercury has these great big cliffs over the surface. They run long distances and they're very steep. And what happened here is, as the planet cooled, it shrank. And it didn't shrink uniformly, is that the crust shrank less than the core did. And so you're left with the crust buckling under effectively under compression and tension. And it causes some parts of it to go underneath others and leaves these large cliffs. All right, so this is an example of the tectonics that have happened. Now, that's not what I want to do that. All right, so we can talk about Mars. Mars is weird. Mars is weird historically. It's not actually all that weird on the ground. But historically, the study of Mars is basically as soon as we had good enough telescopes, we looked at Mars, and Mars has weather. It has dust storms. And so it's not always clear what's going on. But in the late 1800s, people looked, and this is kind of a weird language story, is there was an Italian astronomer, who I don't remember off the top of my head, who saw features on the surface of Mars. And it kind of looked like the picture on the left. And he used a word, canali, for the sort of rough lines that he saw in his image. Now, this is going through translation to other astronomers, and Percival Lowell gets the idea that they're actual canals and starts mapping them. And eventually, the weather clears up on Mars, and astronomers have better telescopes, and they look, and there's no such things there. Like, he comes up with this map of lots of different canals that just aren't there. So, Mars is interesting. It seems like a reasonable place to explore, and it's not too hot. It's not, it's a place where we can send robots and they'll survive. And so we've done a lot of sending robots to Mars and exploring. And what we found is a lot of what, we can see with telescopes, but up close and a better understanding. There's signs of tectonics, of volcanism, of lots of impact crater. You can see from this image, there's lots of cratering in certain areas and minimal cratering in others. So you're seeing signs of lava flows or possibly erosion. There's a region that's bulged out as tectonics. There's volcanoes. There's lots of stuff here. All right. And so a lot of the early craters have been erased, but there is areas with lots of craters. There's lots of shield volcanoes, including Olympus Mons, which I've talked about before. They're growing to be quite big volcanoes. There's valleys and bulges, which are the effect of not plate tectonics, just stretching of the surface. But the most interesting stuff tends to be the signs of erosion because they seem to be water erosion. Right? And so there's places that look like riverbeds that are now dried up. There's places where craters look like they were filled with water, and rocks that normally on Earth form underwater, they appear to have formed on Mars as well, like this. There's places where the hydrogen content can be mapped and it's significant. There's more water ice than other forms of ice. There's places where there appears to be quite young water flows. And of course, this is a fair amount of old information. I'm sure that if you went and researched, you would find newer information. The current theory seems to be that most of the water on Mars is frozen, but it's frozen near the surface and at the poles. And sometimes an area will heat up enough that the water will melt and flow out and then refreeze. And so you get small moments of liquid water on the surface flowing and eroding the surface, and then it refreezes back. So Venus, Venus was very hard to study because it's covered in clouds, and the clouds are hard to see through. You basically have to do radar mapping to find the surface. And so here's what we tend to understand about about the surface here. There's impact craters, but very, very few of them. For one thing, the atmosphere is very good at burning up many of the small objects that would impact. There's volcanoes, both shield and stratovolcanoes. And there's tectonics. There's fractured bits of the surface. And there's signs of erosion, but not very much. It's basically, we've managed to get a couple of things on the surface to look at rocks, and the rocks are pretty uneroded. Maybe a small amount. There's not a lot of wind, and there's no water. So there's not a whole lot that can happen to move the rock around. And so we don't think Venus has plate tectonics, but there's something going on. And basically, we don't see evidence of any surface that's older than about 750 million years. It's basically been repaved in some way. And so something has happened, but we're not sure what's going on. We're not sure if it's weak convection because there's less energy for some reason, or if the material is more viscous, it's thicker, or somehow more rigid. We're not certain of what the deal is, at least at the time that these slides are made. I certainly sent you some articles about ideas on that, but let's see. So the Earth is unique in that it has plate tectonics, and we can measure the motion of the continents. It's on the order of a few centimeters every century. And then the idea, we kind of come up with it late, that the continents look kind of puzzle-like. And what's happening is the continents were together at one time, and new material is formed where they're separating apart. where the seafloors are spreading. And you can kind of, you can look at the difference between continental crust and seafloor crust. And generally, the seafloor is quite young and the continents are older. So seafloor can be recycled. Basically, one plate goes over another, and in those areas where there's subduction, you'll likely see volcanoes and earthquakes a lot. Um, you can see where geological features form. You can see uh, different uh, different stages of the formation. Where the effects of the plate tectonics acting on the continent. Um, you can see the sort of the original ancient land up here in northern Canada, and then go back here where there's mountains. It's going to be lots of collisions with other continents, places where sediment has formed and laid rocks in, and then on the west coast where you have subductions forming new mountains and volcanoes. And there's other places. The Himalayas are a collision between plates that is forcing the mountains upwards, and they are very young mountains. All right, the Appalachians formed in the same way, but much earlier, and so they're much older, much more eroded mountains. There's places where the plates are pulling apart, like the Red Sea, uh, the Rift Valley in East Africa. Places where there's lots of earthquakes. The East Asian and West Coast areas form lots of earthquakes and volcanoes. Effectively, plate boundaries, the Pacific plate and the North American plate and the Asian plates. And so the layout and measurements of plates give us an idea of what the Earth looked like long ago and what it might look like in the future. There's a few other things that come up when a plate moves over a warm area. You can have lava flow that builds up islands, and the Hawaiian Islands are an example of this. Is that over time islands have formed because the Pacific plate has drifted over a warm spot. So this is the thing. If you noticed, we're on Earth, and it's kind of ideal for us. And we're like, well, is this kind of just a special thing, right? Um, what could change? What's the important variables here? And a lot of what we see on Earth is based on its size and its rotation and the distance from the sun. And a lot of other stuff we're not certain of. We don't know why the Earth has plate tectonics and nothing else seems to. Right. So that's going to conclude that. That is the geology chapter for the terrestrial planets. So coming up, I'm going to talk about atmospheres. Um, and it's going to be kind of the same sort of thing. We're going to look at the properties of a generic atmosphere and then the properties of the planets. All right, how do I stop this? Where's the mouse? There's the mouse.